October 19th, 2017. You're staring at telescope data that makes no sense. An object just appeared in our solar system moving 26 kilometers per second. Wrong direction, wrong speed, wrong everything. It's not from here. You've just discovered Oumuamua, the first confirmed visitor from another star system. But before you can study it properly, it vanishes back into the cosmic dark. You had one chance. You missed it. 2 years pass. August 30th, 2019. Another one arrives, this time you're ready. 2I/Borisov, a comet with a tail, behaving exactly as expected. Relief washes over you. Interstellar objects are just comets. Mystery solved. Or so you thought. January 2025. Your screen lights up with something impossible. A third visitor. 3I/Atlas. But this one glows in colours you've never seen on any comet. Its plume stretches 10,000 kilometres across space, and its jets are firing in patterns that shouldn't exist. 3 visitors. 3 radically different objects. The first was a mystery we couldn't solve. The second was a comet we understood. The third is changing everything. If this is exactly the kind of cosmic mystery you crave, smash that like button and subscribe. These deep dive space investigations take serious time to research and craft. When you hit like and subscribe, you're telling us, give me more of this. And ring that bell, the universe doesn't wait. Until 2017, humanity had never seen an object from another star system. Think about that for a moment. We'd been studying the cosmos for centuries, mapping planets, tracking asteroids, cataloguing comets, but every single object we'd ever observed was born here. In our solar system, orbiting our sun, we were cosmically isolated, studying only our own neighbourhood, never catching a glimpse of what lay beyond. The tools were there, telescopes powerful enough to spot city-sized rocks millions of miles away, computer systems that could calculate orbital trajectories with ridiculous precision, a global network of astronomers watching the sky every single night. But interstellar objects, they were theoretical, mathematical curiosities. Scientists knew they had to exist after all. Our solar system ejects objects into interstellar space. So other star systems must do the same. But actually finding one, the odds seemed impossible. Here's why. Space is incomprehensibly vast. The nearest star system, Alpha Centauri, sits 4.37 light-years away. That's 25 trillion miles. And interstellar objects don't light up like stars or reflect light like planets. They're dark, cold, typically no bigger than a mountain, hurtling through an ocean of darkness at speeds that would take them across the entire United States in less than 3 minutes. Finding one passing through our solar system would be like spotting a single black pebble thrown past your window while you're standing in a football stadium. At night, during a rainstorm. But on October 19th, 2017, astronomers using the Pan-STARRS 1 telescope in Hawaii noticed something odd in their nightly scan. A faint dot of light moving against the background stars. Standard procedure, they flagged it for follow-up observations. Maybe another asteroid, maybe a comet. Probably nothing special, except when they calculated its trajectory, everything changed. The object was moving at 26 kilometers per second relative to the Sun. That's 58,000 miles per hour. Fast, but not unprecedented. What stunned them was the shape of its orbit, a hyperbola. You see, objects born in our solar system follow elliptical orbits, looping around the Sun in predictable patterns. Comets, asteroids, planets, they're all trapped by the Sun's gravity, circling endlessly like water spiralling down a drain. But a hyperbolic orbit is different. It's an open curve. The object comes in, swings past the Sun once, and shoots back out into interstellar space, never to return. This thing wasn't circling, it was passing through. Within days, telescopes around the world swiveled to track it. The Hubble Space Telescope, the Gemini Observatory, the Very Large Telescope in Chile. They watched it tumble end over end, rotating every 7.3 hours. They measured its brightness fluctuations wildly variable, suggesting an extremely elongated shape. Initial estimates put it at roughly 400 meters long and only 40 meters wide, a ratio of 10 to 1. Nothing in our solar system looks like that. Our asteroids are lumpy potatoes. Our comets are dirty snowballs. This was a cosmic cigar. Karen Meach, the astronomer leading the Discovery team, told reporters, "For decades we've theorized that such interstellar objects are out there, and now for the first time we have direct evidence they exist." The International Astronomical Union gave it an official designation one E/2017 U1. The I stood for Interstellar, a brand new classification created specifically for this object. But the Discovery team also gave it a Hawaiian name, Oumuamua, meaning a messenger from afar arriving first. A messenger. That's exactly what it was, the first tangible proof that we're not isolated. Other star systems are out there, and they're sending objects our way, whether intentionally or not. But here's the tragedy. By the time astronomers realized what they were looking at, Oumuamua had already passed its closest approach to the Sun. It was already racing away, back toward interstellar space, picking up speed as the Sun's gravity flung it outward like a slingshot. Researchers had weeks at best to study it before it faded from view forever. Weeks to answer questions that had been building for decades. They scrambled. Every available telescope pointed at that fading speck. They measured its spectrum, analysing the sunlight reflecting off its surface to determine composition. They tracked its trajectory with obsessive precision, plotting its path backward through time to figure out where it came from. The data suggested it had been travelling through interstellar space for hundreds of millions of years, possibly longer. Tracing its origin proved nearly impossible after that much time. The motion of stars themselves made it unclear which system had ejected it. And then came the anomaly. As Oumuamua sped away from the Sun, astronomers noticed it was accelerating not by much, but measurably more than could be explained by the Sun's gravity alone. This is normal for comets. As they heat up near the Sun, ice vaporizes, creating jets of gas that act like tiny rocket engines, pushing the comet slightly off course. But Oumuamua showed no visible tail, no gas jets, no outgassing at all. So what was pushing it? Scientists proposed explanations. Maybe it was outgassing hydrogen invisible to our telescopes. Maybe its surface was shedding dust too fine to detect. Maybe we'd miscalculated its trajectory. But none of the explanations felt completely satisfying. Harvard astronomer Avi Loeb went further, suggesting controversially that the acceleration could indicate artificial origins. Perhaps a light sail, a sheet of reflective material pushed by starlight. The scientific community largely dismissed this, but the seed of mystery was planted. By December 2017, Oumuamua had faded beyond detection. Gone. We'd had roughly 10 weeks to study the first confirmed visitor from another star system, and we'd barely scratched the surface. No spacecraft had been sent to intercept it. We'd had no time to plan. No mission ready to launch. It arrived unannounced and left before we could say goodbye. But it had changed everything. Astronomers now knew interstellar visitors weren't just theoretical, they were real. They were detectable, and they could show up at any time. The question wasn't if another would arrive. The question was when, and whether we'd be ready. You didn't have to wait long. 22 months later, on August 30th, 2019, a telescope in Crimea detected something new, and this time, astronomers caught it early. What they found was both familiar and revolutionary. and it would test everything they thought they'd learned from Oumuamua. Gennady Borisov wasn't supposed to make history. He's an amateur astronomer, telescope engineer by profession who built his own 0.65-metre telescope in his backyard in Crimea. No university funding, no research team, just a man who loved watching the sky. On the night of August 30th, 2019, he was doing what he'd done hundreds of times before scanning for comets, asteroids, anything interesting passing through our cosmic neighbourhood. Then he spotted something moving. At first glance, it looked like a typical comet, a fuzzy blob with a faint tail. Exactly what you'd expect from a chunk of ice and rock warming up as it approached the sun. He logged the observation and submitted it to the Minor Planet Center, the official clearinghouse for asteroid and comet discoveries. Routine procedure. He probably figured it was just another local comet, one of thousands that loop through the inner solar system. But when other astronomers began tracking it, calculating its trajectory, the numbers didn't add up. This object was moving at 32 kilometers per second relative to the Sun, that's over 71,000 miles per hour. And just like Oumuamua before it, its orbit was hyperbolic. It wasn't from here. Gennady Borisov, working alone with homemade equipment, had just discovered the second interstellar object in human history. Think about that. The first interstellar visitor was found by one of the most advanced telescope systems on the planet, Pan-STARRS, a $100 million facility designed specifically to scan the entire sky every night. The second was found by a guy in his backyard. It's one of those beautiful reminders that in astronomy, you don't need $1 billion budget to change our understanding of the universe. You just need patience, clear skies, and a decent telescope. The International Astronomical Union designated it 2I/Borisov, the 2I, marking it as only the second confirmed interstellar object ever detected. But unlike Oumuamua, which had already been leaving when we found it, Borisov was discovered early, still approaching the Sun. Astronomers had months to study it. Months to point every major telescope on Earth and in orbit directly at this visitor from another star system. And what they saw was almost anticlimactic. Almost. Borisov looked like a comet, a completely normal, unremarkable comet. It had a visible coma, that fuzzy cloud of gas and dust surrounding the nucleus. It had a tail stretching behind it, blown back by solar wind and radiation pressure. It was outgassing water vapor, carbon monoxide, and cyanide, exactly what you'd see from any comet born in our own solar system. Spectrographic analysis showed dust grains consistent with silicates and organic compounds. Everything about it screamed comet. Astronomers using the Atacama Large Millimeter Array in Chile detected carbon monoxide in its coma at concentrations similar to comets formed in the coldest, outermost regions of our solar system. Hubble Space Telescope observations measured the size of its nucleus roughly 500 meters across, about half a kilometer. Smaller than Oumuamua, but well within the normal size range for comets. So why was this such a big deal? Because normal was exactly what scientists needed. Oumuamua had been weird, that bizarre elongated shape. The unexplained acceleration. No visible outgassing. It raised more questions than it answered. Was it a fluke? Were all interstellar objects strange? Did we just not understand how objects from other star systems behaved? Borisov answered those questions with a resounding no. Interstellar objects can be perfectly ordinary. Piotr Guzik from Jagiellonian University, who led one of the observation teams, put it perfectly. Borisov is the first known interstellar object that is unambiguously active. A real comet, and it looks nothing like Oumuamua. Its properties are remarkably similar to those of comets in the solar system. That similarity is profound. It means the processes that form comets around other stars, planet formation, icy material condensing in the outer reaches of solar systems, gravitational interactions, flinging objects into interstellar space, those processes are universal. The physics works the same way everywhere. Borisov was proof that our solar system isn't special. What happens here happens out there, around other stars, in other systems scattered across the galaxy. But here's where it gets really interesting. While Borisov looked normal overall, subtle details revealed it came from somewhere fundamentally different. Observations from the European Southern Observatory's Very Large Telescope detected unusually high concentrations of carbon monoxide in its coma, significantly higher than typical solar system comets. This suggested Borisov formed in an extremely cold environment, possibly in the outer regions of its home star system where temperatures barely rise above absolute zero. Scientists also noticed Borisov's nucleus was surprisingly red, a deep crimson colour indicating its surface was rich in organic compounds that had been altered by cosmic radiation over millions of years of interstellar travel. That radiation exposure, that journey through the void between stars, had marked it, changed it in ways that separated it from comets that spent their entire existence within the protective bubble of a single star system. Can you imagine the journey this thing took? Borisov likely formed around another star billions of years ago, during the chaotic early days of that system's planetary formation. Something, probably a Jupiter-sized planet, gravitationally kicked it out, sending it tumbling into the cold dark between stars. It travelled for millions, possibly hundreds of millions of years, alone in the void, bombarded by cosmic rays, never seeing another star up close, until it wandered into our solar system by pure chance, and a telescope engineer in Crimea happened to be looking at exactly the right patch of sky at exactly the right time. By late 2019 and into early 2020, Borisov became one of the most observed objects in astronomy. The Hubble Space Telescope tracked it continuously. Ground-based observatories from Hawaii to Chile followed its every move. Scientists published dozens of papers analysing its composition, trajectory, and behaviour. They watched as it reached perihelion, its closest approach to the Sun, on December 8, 2019, passing within 2 astronomical units, roughly twice the distance between Earth and the Sun. And then, just like Oumuamua, it began its exit. By mid-2020, Borisov had dimmed beyond the reach of most telescopes, fading back into the cosmic ocean from which it came. We'd studied it for nearly a year, far longer than Oumuamua, but eventually it too disappeared, continuing its lonely journey through interstellar space. 2 visitors, 2 completely different experiences. The first was a mystery wrapped in an enigma that escaped before we could solve it. The second was familiar, comfortable, a cosmic confirmation that the universe operates on consistent principles. Scientists felt confident they understood what they were seeing. Interstellar objects, they concluded, were just comets and asteroids from other star systems. Interesting. Yes. Revolutionary for astronomy. Absolutely. But ultimately explainable within existing frameworks. Then January 2025 arrived, and everything they thought they understood shattered. Because the third visitor wasn't like the first, and it definitely wasn't like the second. It was something else entirely, something that's forcing scientists to question whether they've been missing something fundamental about what travels between the stars. The Atlas Survey System Asteroid Terrestrial Impact Last Alert System runs automatically, scanning the sky every night from observatories in Hawaii, Chile, and South Africa. Is designed to catch near-Earth asteroids that might pose impact threats, churning through millions of data points, flagging anything unusual for human review. On a January night in 2025, the system triggered an alert, an object moving on a hyperbolic trajectory, fast, bright, and already inside the orbit of Jupiter, within hours. Confirmation came from observatories worldwide. We had our third interstellar visitor. The designation came quickly, 3I/Atlas. the third confirmed object from beyond our solar system. But the moment astronomers turned their telescopes toward it, they knew something was different. It was glowing, not just reflecting sunlight like a normal asteroid or producing a standard white-blue coma like Borisov. This thing was emitting light in multiple colours, simultaneously reds, greens, blues, all swirling together in a cosmic light show nobody had ever witnessed on a comet before. Spectrographic analysis showed emission lines corresponding to different molecular species, each one glowing at its own distinct wavelength as it vaporized and fluoresced under solar radiation. Then they measured the plume, 10,000 kilometers across. That's wider than Earth's diameter of 12,742 kilometers. For context, when Borisov was at peak activity, its coma measured roughly 130,000 kilometers across. Impressive, but diffuse, spread thin. 3I/Atlas's plume is denser, more concentrated, more energetic. It's not just outgassing, it's erupting. Dr. Michelle Bannister from the University of Canterbury, monitoring the object through New Zealand's telescopes, described the initial observations. We're seeing activity patterns that don't match our models for cometary behaviour. The multi-wavelength emissions suggest simultaneous outgassing of multiple volatile species water, carbon monoxide, ammonia, possibly methane, all at rates that seem disproportionate to the object's estimated size. And that size current estimates put 3I/Atlas at roughly 1 to 2 kilometers in diameter. That makes it significantly larger than both previous interstellar visitors. Oumuamua was about 400 meters long. Borisov's nucleus was around 500 meters. This is potentially 4 times bigger, more mass, more surface area, more material to outgas. But even accounting for that, the activity levels seem extreme. What's driving this? The leading hypothesis involves the object's composition and its interstellar journey. Imagine you're a comet-sized chunk of ice, rock, and frozen gases, ejected from your home star system millions of years ago. You spend eons drifting through interstellar space where temperatures hover just a few degrees above absolute zero. We're talking minus 270 degrees Celsius, minus 454 Fahrenheit. At those temperatures, even gases like carbon monoxide and nitrogen freeze solid. Now you wander into a new solar system. The temperature starts rising. Slowly at first, then faster as you approach the star. Those ultra-volatile ices materials that have been frozen solid for millions of years suddenly start sublimating, transforming directly from solid to gas. It's not a gentle process. It's explosive. Pockets of trapped gas burst through the surface. Jets fire in multiple directions. And if you're loaded with different types of ice's water here, carbon monoxide there, ammonia somewhere else, they all vaporize at different temperatures, creating that multicolored glow as each molecule fluoresces under ultraviolet radiation from the sun. But here's what's keeping astronomers up at night: the jets aren't random. High-resolution imaging from observatories equipped with adaptive optics shows the outgassing is directional, concentrated into discrete jets firing from specific locations on the object's surface. And those jets are massive, some extending thousands of kilometers into space before dissipating. This isn't unprecedented. Comets in our solar system produce jets too. Comet 67P/Churyumov-Gerasimenko, visited by the Rosetta spacecraft, displayed multiple jets erupting from its surface. But 67P is a thoroughly studied comet that's made hundreds of passes around the Sun. We understand its behaviour because we've watched it repeatedly. 3I/Atlas is brand new to our solar system, coming from God knows where, and it's already more active than most comets we've ever observed during their first approach. There's another detail that has everyone talking its trajectory. 3I/Atlas is approaching the Sun at an angle that will bring it relatively close, though Close, in astronomical terms, still means tens of millions of kilometers. Current projections suggest it will reach perihelion sometime in the coming months, at which point solar heating will intensify and the already extreme outgassing will likely increase even further. This raises an obvious question: will it survive? Some comets don't. They get too close to the sun, the heating becomes too intense, and they literally tear themselves apart. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before slamming into Jupiter in 1994. Comet Ison in 2013 disintegrated as it grazed past the Sun. Could 3I/Atlas suffer the same fate? Possibly. Its extreme activity suggests it's structurally fragile, perhaps a loosely bound collection of icy chunks held together by weak gravity and frozen materials acting like glue. As it heats up and outgasses violently, that structural integrity could fail. If it breaks apart, we'd witness something unprecedented, an interstellar object fragmenting in real time, potentially revealing what's inside, giving us a cross-section view of material formed around another star. Or it might hold together. Size helps. Larger objects have stronger self-gravity. If 3I/Atlas is indeed 1 to 2 kilometers across, that might be enough mass to keep it intact even under severe outgassing stress. We're about to find out. The scientific community is mobilizing like never before. The James Webb Space Telescope has allocated observation time to study 3I/Atlas in infrared wavelengths, which can penetrate the dusty coma and potentially glimpse the nucleus directly. Ground-based observatories across 6 continents are coordinating continuous monitoring campaigns. Radio telescopes are searching for emissions from complex organic molecules. Even amateur astronomers with decent equipment can spot a fuzzy, multicolored smudge moving against the background stars. Can you see it from your backyard? If you've got a good telescope and dark skies? Possibly. It's not naked eye visible, but observers with 8-inch or larger telescopes have reported successfully imaging it. There's something deeply poetic about that, an object that travelled for millions of years through the void between stars, visible to anyone willing to look up. But visibility creates urgency, unlike Oumuamua, which was discovered on its way out, and unlike Borisov, which gave us months of advance warning. 3I/Atlas is moving fast and we're catching it mid-approach. Every night of observation counts, every data point matters, because once it swings past the sun and heads back into interstellar space, it's gone forever. And scientists are racing to answer a question that becomes more pressing with every new observation. Is 3I/Atlas just an unusually active comet? Or is there something fundamentally different about interstellar objects that we're only now beginning to understand? To answer that, we need to look at what makes these 3 visitors truly different from each other, starting with where they came from and how they got here. Tracing the origin of an interstellar object is like being a detective investigating a crime that happened millions of years ago, where the suspect has been wandering aimlessly through a constantly shifting landscape, and all the witnesses have moved to different cities. It's astronomically difficult, literally. Start with Oumuamua, when astronomers plotted its trajectory backward through time. They found it was moving roughly from the direction of the constellation Lyra, near the bright star Vega. Your first thought might be, great, it came from Vega, but space doesn't work that way. Vega is 25 light-years away, even at Oumuamua's speed of 26 kilometers per second, blazingly fast. By our standards, it would take roughly 450,000 years to cover that distance. And here's the problem. Stars move. Vega isn't stationary. It's orbiting the galactic center just like our Sun, moving through space at about 20 kilometers per second relative to the local standard of rest. So 450,000 years ago, Vega wasn't where it is now. Neither was our Sun. Neither were any of the nearby stars. when you rewind the positions of stars over hundreds of thousands of years, accounting for their individual motions through the galaxy, the picture becomes hopelessly blurred. Oumuamua's path crosses through regions of space that dozens of star systems have passed through at various times. A 2018 study published in the Astronomical Journal by Baylor Jones and colleagues traced Oumuamua's trajectory back through time, accounting for the galactic gravitational field and the motion of nearby stars. Their conclusion: the closest they could narrow it down was 4 possible dwarf stars that Oumuamua might have passed within a few light years of roughly 1 million years ago. Might have. But even those aren't necessarily its origin point, just places it passed near during its journey. Its actual birthplace, unknown, possibly unknowable. Think about what that means. This object could be billions of years old, ejected from its home star system when that system was still forming planets, and it's been wandering the galaxy ever since. It could have passed near hundreds of stars. It could have crossed through multiple spiral arms of the Milky Way. By the time it stumbled into our solar system, any trace of its origin had been erased by time and distance. Now consider 2I/Borisov. Same problem, different direction. It approached our solar system from the direction of the constellation Cassiopeia, moving at 32 kilometers per second relative to the Sun, faster than Oumuamua. Researchers at the European Space Agency's Near-Earth Object Coordination Center ran simulations tracing its path backward. The best candidate they found was a red dwarf star designated Kruger, 60 located about 13 light-years away. At Borisov's speed, that journey would take roughly 130,000 years. But again, best candidate doesn't mean certainty. Kruger 60 is simply one of several stars whose past positions align reasonably well with Borisov's trajectory when you account for stellar motion and gravitational perturbations. It's an educated guess. Piotr Dybszynski from Adam Mickiewicz University, who worked on trajectory reconstructions, noted that tracing back over such timescales introduces cumulative uncertainties that make definitive origin identification essentially impossible with current methods. And 3I/Atlas. We're still gathering data. Its trajectory is being calculated now, in real time, as it moves through our solar system. Preliminary analyses suggest it's approaching from yet another direction entirely, neither from Lyra like Oumuamua nor from Cassiopeia like Borisov. The early velocity estimates put it somewhere around 35 to 40 kilometers per second relative to the Sun, making it the fastest of the 3 visitors. Here's what's fascinating. These 3 objects are coming from completely different directions. That tells us something profound about the distribution of interstellar objects. They're not streaming from one particular source. They're not all coming from one nearby star-forming region or one disrupted planetary system. They're coming from everywhere. The galaxy is apparently filled with these wanderers, travelling in all directions, ejected from countless different star systems over billions of years. How many are out there? That's the trillion-dollar question. Literally. Before Oumuamua, estimates for the density of interstellar objects in our galaxy were pure speculation. After detecting just one, astronomers revised their estimates upward. After Borisov, they revised again, and with 3I/Atlas now in view, the numbers keep climbing. Current estimates, based on detection rates and accounting for observational biases, suggest there could be thousands of interstellar objects passing through the inner solar system at any given time. Thousands. Most are too small or too dark to detect. We're only spotting the largest, brightest ones, the cosmic equivalent of seeing only the biggest ships passing through a harbour, while hundreds of smaller boats go unnoticed. David Jewett, a planetary scientist at UCLA who's studied all 3 interstellar visitors, put it bluntly in a 2023 paper. The interstellar object population appears to be far more abundant than previously thought. For every one we detect, there are likely hundreds we miss. The space between stars is not empty, it's a highway. A highway. Picture that for a moment. Right now, as you're watching this, multiple interstellar objects are probably passing through our solar system. Some near Jupiter, some between Mars and Earth. Some might even be closer than the Moon. We just don't see them because they're not big enough, not bright enough, or we're not looking in the right direction at the right time. But here's where it gets really interesting. Speed matters. Not just for calculating trajectories, but for understanding what these objects can tell us. Oumuamua at 26 kilometers per second, Borisov at 32, 3I/Atlas potentially near 40. These speeds tell us about the environments they came from. Objects ejected from tightly bound star systems where planets orbit close to their star tend to be flung out at lower speeds. Objects from loosely bound systems where planets orbit far from their star can achieve higher ejection velocities. The speed also tells us about what ejected them. A close gravitational encounter with a Jupiter-mass planet might impart 20 kilometers per second. An encounter with something more massive, a brown dwarf or a companion star in a binary system, could launch an object at 50 or 60 kilometers per second. So when we measure these speeds, we're not just tracking where they're going, we're learning about the types of planetary systems that ejected them, the architecture of those distant solar systems, the masses of the planets involved. Each velocity is a clue, a piece of forensic evidence from a crime scene billions of miles and millions of years away. And the trajectories themselves, those hyperbolic arcs, they're not perfectly smooth. Gravitational interactions with planets in our solar system bend them. Jupiter, with its immense mass, can deflect an interstellar object by several degrees. Saturn adds its own perturbation. Even Earth's gravity, tiny by comparison, contributes microscopically to the path. Astronomers have to account for all of this when calculating where these objects came from and where they're going. It's not just three-body physics, it's 10-body physics, the Sun, 8 planets, and the visitor all pulling on each other simultaneously. The math is brutal, the uncertainties compound, but the effort is worth it because hidden in those trajectories is the story of how these objects travelled across the galaxy to find us. That journey, that incredible voyage through interstellar space, shapes everything about what we see when these visitors arrive. It determines their composition, their activity, their appearance. And when you compare all three side by side, really examine what they look like and what they're made of, the differences become even more striking than the similarities. Put the three objects side by side and they look like they came from three completely different universes. Oumuamua first. Shape alone sets it apart. That 10:1 length-to-width ratio makes it the most elongated natural object ever observed in our solar system or from outside it. Imagine a cosmic skyscraper tumbling through space, roughly 400 meters long and only 40 meters wide. For comparison, that's about the length of 4 football fields but only as wide as a single goalpost. Nothing we've seen in nature looks like that. Well, almost nothing. Asteroid 1566. Icarus has an elongated shape, maybe 3:1. Some contact binary asteroids, 2 rocks stuck together, can reach 2:1, but 10:1, that's unprecedented. It's so extreme that some researchers initially questioned whether the brightness variations, which is how we inferred the shape, might be caused by something else. Maybe an irregular albedo pattern, maybe unusual surface composition creating brighter and darker patches. But multiple independent analyses confirmed it. Oumuamua is genuinely that elongated, and the colour spectroscopic observations showed it has a distinctly reddish tint. Alan Fitzsimmons from Queen's University Belfast, who led a spectroscopy team studying it, described the surface as consistent with an organic-rich composition exposed to cosmic rays for hundreds of millions of years. That reddish colour comes from complex organic molecules, carbon-based compounds, that have been irradiated and chemically altered during its long interstellar journey. Think of it like cosmic rust. But instead of oxidized iron, you've got irradiated hydrocarbons. But here's the kicker despite that organic-rich surface. Oumuamua showed no detectable outgassing, no coma, no tail, nothing. When the Spitzer Space Telescope searched for carbon-based gases or dust grains, it found nothing. When radio telescopes looked for molecular emissions, they detected silence. It looked inert, dead, like a tumbling shard of rock coated in ancient organic gunk. Now compare that to 2I/Borisov, completely different animal. Borisov is round, or at least roundish. Nucleus estimated at 500 meters in diameter, making it slightly larger than Oumuamua in terms of volume despite being shorter. And where Oumuamua was dark and inactive, Borisov was bright and violently alive. The coma surrounding Borisov stretched up to 130,000 kilometers across, at peak activity roughly 10 times Earth's diameter. That's not just impressive. That's a flag screaming I'm a comet, visible from millions of kilometers away. The tail extended even farther, blown back by solar radiation pressure, streaming behind it like cosmic hair in the wind, and the composition water vapor dominated, with significant amounts of carbon monoxide, cyanide, and diatomic carbon detected by multiple observatories. Adam McKay from NASA's Goddard Space Flight Center analyzed data from the Keck Observatory and found that the gas production rates and composition ratios in Borisov closely match comets from the Oort cloud, the most primitive objects in our solar system. But remember those unusually high carbon monoxide concentrations. That's where Borisov showed its interstellar origins. Solar system comets typically have CO to water ratios between 1% and 30%. Borisov's ratio pushed toward the high end of that range, suggesting it formed in extremely cold conditions, colder even than the outer reaches of our solar system. We're talking temperatures where even carbon monoxide, which boils at minus 191 degrees Celsius, freezes solid. The colour was also telling. Like Oumuamua, Borisov's nucleus appeared reddish, that telltale sign of organic compounds altered by cosmic radiation. But unlike Oumuamua, we could see past that surface layer because of all the outgassing, which gave us a window into its interior composition. It was like slicing open an apple to see what's inside, except the apple was slicing itself open through its own activity. Then there's 3I/Atlas, and honestly it defies easy categorization. Size-wise, it's the giant of the group. 1 to 2 kilometers in diameter means it has roughly 4 to 16 times the volume of Oumuamua, depending on its actual dimensions. More mass, more gravitational self-compression, more internal material that's been protected from cosmic radiation. If you could somehow place all three objects together, 3I/Atlas would dwarf the other two. The shape unknown. We're still gathering data. High-resolution imaging is difficult because of that massive bright plume obscuring the nucleus. It's like trying to photograph a light bulb surrounded by a glowing fog. Adaptive optics systems are working to peer through the coma, but so far we haven't gotten a clear view of the actual nucleus shape. But the activity, that's where 3I/Atlas becomes genuinely bizarre. That multicoloured glow isn't just pretty, it's diagnostic. Each colour corresponds to specific molecules fluorescing at characteristic wavelengths. The reds suggest emissions from carbon-based molecules, possibly CN-cyanogen or C2 diatomic carbon. The greens typically come from diatomic carbon at different energy states. Blues might indicate CO plus ions or other species. What makes this remarkable is that we're seeing all of these emissions simultaneously, and at intensities that suggest massive outgassing rates. Dr. Matthew Knight from the US Naval Academy, who's been monitoring 3I/Atlas through the Lowell Discovery Telescope, noted in preliminary observations that the brightness and spectral complexity exceed what we typically see in new comets making their first approach to the Sun. This level of activity in an object we're only now detecting suggests either an unusually volatile composition or structural fragmentation releasing buried ices. That plume 10,000 kilometers across is dense enough to be visible in moderate-sized telescopes from Earth's surface. For comparison, when Halley's comet approached the Sun in 1986, its coma peaked at roughly 100,000 kilometers. But Halley is a known, predictable comet that's made dozens of passes through the inner solar system. 3I/Atlas is on its first ever approach to our Sun, potentially its first approach to any star in millions of years, and it's already producing a plume that's proportionally more massive relative to its size. And those JET's ground-based observations equipped with adaptive optics have resolved at least 4 distinct jet structures emanating from the nucleus. They're not symmetrically distributed. They appear to be erupting from discrete active regions on the surface, specific patches where subsurface ice is being heated and explosively sublimating. Here's why that matters. When solar radiation heats a comet, it doesn't heat uniformly. The side facing the Sun gets cooked. The night side stays cold. As the object rotates, different regions heat up and cool down, creating thermal stress. On a typical comet, this produces a few jets, maybe half a dozen, but 3I/Atlas is showing complex, multiple jet activity that suggests either rapid rotation, unusual surface composition with different ice reservoirs at varying depths, or structural weaknesses where material is venting preferentially. So let's recap what we're looking at. Oumuamua elongated, inactive, reddish, mysterious. Borisov round, highly active, compositionally similar to solar system comets but with subtle differences. 3I/Atlas large, explosively active, spectrally complex, structurally unknown, 3 visitors, 3 wildly different presentations. And that diversity raises an uncomfortable question. Are we looking at 3 different types of objects? Or are we looking at 3 different stages of the same type of object? Could Oumuamua have once been as active as 3I/Atlas, but lost all its volatile ices during previous encounters with stars? Could Borisov eventually become dark and inert like Oumuamua after millions more years wandering the galaxy? Or, and this is where things get controversial, could one of these objects be something other than a natural comet or asteroid? Because the physical differences between them are so stark that some scientists have started asking questions that most astronomers prefer to avoid. Questions about whether natural processes alone can explain everything we're seeing. The controversy started within days of Oumuamua's discovery. That non-gravitational acceleration, the fact that it was speeding up in ways that couldn't be explained by the Sun's gravity alone, became the spark that ignited one of the most heated debates in modern astronomy. Avi Loeb saw something nobody else wanted to see. Loeb is chair of Harvard's astronomy department, former chair of the advisory board for the Breakthrough Starshot Initiative, and one of the most published astronomers alive. He's not a fringe scientist, he's establishment. But in 2018 he co-authored a paper in the astrophysical journal Letters that sent shockwaves through the scientific community. The paper proposed that Oumuamua's acceleration could be explained if it were a light sail, a thin, reflective sheet designed to be pushed by starlight, possibly an artificial probe sent by an extraterrestrial civilization. The reasoning went like this: for radiation pressure from sunlight to significantly accelerate an object, that object needs to be extremely thin relative to its surface area. Think of a sail on a ship, lots of surface area, minimal thickness. Loeb calculated that if Oumuamua were less than a millimeter thick with that elongated shape, solar radiation pressure could account for the observed acceleration. and a millimetre-thick object 400 metres long. That's not natural. That's engineered. He told The Guardian in a 2021 interview, "The reason I contemplate an artificial origin is because of Oumuamua's peculiar properties. Scientifically, we should consider all possibilities, even if they seem unlikely." The astronomical community responded with something between skepticism and outrage. Not because they thought aliens were impossible, but because Loeb had jumped to an extraordinary conclusion without exhausting ordinary explanations. In science, you don't invoke alien technology when natural processes might still explain what you're seeing. It's called Occam's razor. The simplest explanation is usually correct. Alternative explanations flooded in. One team proposed Oumuamua could be a hydrogen iceberg, an object coated in frozen molecular hydrogen. As it warmed near the sun, that hydrogen would sublimate, creating thrust without producing a visible coma because hydrogen is transparent. Another group suggested it could be nitrogen ice, similar to the surface of Pluto's Sputnik Planitia region. Nitrogen ice would also sublimate without creating visible outgassing. Both explanations had problems. Hydrogen icebergs are theoretically possible but have never been observed, and it's unclear how they'd form. Pure nitrogen ice requires very specific formation conditions and would likely have completely vaporized during Oumuamua's close approach to the sun. Neither explanation felt bulletproof. But here's the key point: just because we don't have a perfect natural explanation doesn't mean the answer is aliens. The universe is full of phenomena we don't fully understand. Jumping to it must be artificial is intellectually lazy. It's the cosmic equivalent of ancient humans seeing lightning and concluding it must be Zeus throwing thunderbolts. Now consider 2I/Borisov. Zero controversy. None. Nobody suggested it was artificial. Why? Because it behaved exactly like a comet. It had a visible coma and tail. It outgassed water and carbon monoxide at rates consistent with natural sublimation. Its orbit, while hyperbolic, showed none of the acceleration anomalies that plagued Oumuamua. Every observation fit neatly into existing models of cometary behavior. The consensus was immediate and unanimous: Borisov is a natural object, a comet ejected from another planetary system, and there's nothing mysterious about it beyond the simple fact that it came from somewhere else. Case closed. That contrast is important. It demonstrates that astronomers aren't reflexively dismissing interstellar objects as natural. When something looks like a comet, acts like a comet, and outgasses like a comet, everyone agrees it's a comet. The controversy around Oumuamua exists precisely because it didn't fit that pattern. But Borisov's normalcy also did something unexpected. It made Oumuamua seem even more anomalous. If interstellar comets look like Borisov, then what the hell was Oumuamua? The more we learned about typical interstellar objects through Borisov, the less Oumuamua made sense. Enter 3I/Atlas. Too early for conclusions, but speculation's already building. On one hand, it looks like a comet. It has outgassing, it has a coma, it's producing jets and a massive plume. All of that screams natural object behaving naturally under solar heating. Nobody's seriously suggesting it's artificial, but on the other hand, that multicolored glow is weird. Those emission spectra don't match typical comets. The activity levels seem disproportionate to its size and distance from the sun. And we're seeing jet structures that don't conform to standard cometary outgassing models. Does that mean it's artificial? No. Does it mean we don't fully understand what's happening? Absolutely does. Dr. Paul Byrne, a planetary scientist at Washington University in St. Louis, who's been following 3I/Atlas observations, put it carefully: what we're seeing challenges our expectations. But challenging expectations isn't the same as defying explanation. Comets are complex objects. Each one teaches us something new. The fact that 3i/Atlas doesn't perfectly match our models might just mean our models need updating. That's the measured scientific response. But let's be honest, measured responses don't trend on social media. Within weeks of 3i/Atlas's discovery, online speculation exploded. Forums buzzed with theories. YouTube videos with titles like "New Interstellar Object Could Be Alien Probe" racked up millions of views. The multicolored globe became evidence of propulsion systems. The jets became exhaust ports. The whole thing spiraled into exactly the kind of unsubstantiated hype that makes scientists cringe. Here's the reality. Distinguishing natural from artificial is genuinely difficult when you're observing something millions of kilometers away with limited data. What criteria would you even use? Artificial objects might emit radio signals, but we checked all 3 interstellar visitors with radio telescopes and found nothing. Artificial objects might show geometric shapes, but we can barely resolve these objects well enough to determine basic dimensions, let alone detect geometric precision. Artificial objects might maneuver, but gravitational interactions and outgassing can mimic maneuvering. The SETI Institute's search for extraterrestrial intelligence pointed radio telescopes at Oumuamua in 2017. They scanned across a wide range of frequencies looking for any artificial signals. Nothing. The Allen Telescope Array did the same. Nothing. If Oumuamua was an alien probe, it was either not transmitting at frequencies we didn't check, or transmitting so weakly we couldn't detect it. But absence of evidence isn't evidence of absence. Right, maybe. But it's also not evidence of presence. This is where the debate gets frustrating. Proponents of the artificial hypothesis point to all the things we don't know and say, "See, it could be aliens." Skeptics point to the same unknowns and say, "See, we just need more data." Both sides are technically correct, but only one approach is scientifically productive. Seth Shostak, senior astronomer at the SETI Institute, framed it perfectly. The fact that we can't immediately explain something doesn't mean we should immediately invoke the most extraordinary explanation. History is littered with phenomena that seemed inexplicable until we developed better instruments or better theories. Aliens should be the last hypothesis we consider, not the first. And yet, the question persists. How would we know if an extraterrestrial civilization sent a probe through our solar system? What would it look like? Would it be a sleek spacecraft like in the movies? Or would it be something completely alien to our expectations, perhaps disguised as a natural object to avoid detection? Or constructed from materials and using technologies we can't even conceive of? That's the uncomfortable truth at the heart of this debate. We genuinely might not recognize an artificial object if we saw one, especially if it was designed by intelligence with millions of years of technological advancement beyond ours. Our assumptions about what artificial looks like are inherently limited by our own level of development. But here's the counter-argument: science doesn't advance by assuming aliens every time something seems weird. It advances by assuming nature is doing something we haven't figured out yet, and then working tirelessly to figure it out. That approach has explained virtually every mystery in the history of astronomy, from planetary retrograde motion to pulsars to fast radio bursts. Why should interstellar objects be different? The real issue isn't whether these objects might be artificial. The real issue is that we're barely scratching the surface of understanding them at all. We're catching fleeting glimpses of visitors passing through at tens of kilometers per second, and we're trying to decode their entire life history from a handful of pixels and spectra. That's the challenge. And it's a challenge that becomes painfully clear when you look at how difficult it is to actually study these things before they vanish forever. Imagine you're an astronomer and you get an alert an interstellar object has just been detected entering the solar system. Your heart races. This is your chance to study something from another star. You immediately start planning observations. Then you check the trajectory data and your excitement collapses into dread. The object is already past Mars. It's moving away, and you have maybe 3 weeks before it's too faint to observe. That was the Oumuamua nightmare. By the time astronomers realized what they were looking at, Oumuamua had already made its closest approach to the Sun on September 9, 2017, a full 40 days before discovery. It had whipped around the Sun, picked up gravitational speed, and was racing back toward interstellar space. The discovery on October 19th was essentially catching it on its way out the door. Robert Werrick, the astronomer at the University of Hawaii who first spotted it in Pan-STARRS data, described the realization, when we calculated the orbit, we knew immediately this was something special. But we also knew we were seeing it too late. It was already at 1.4 astronomical units from the Sun and receding fast. Every hour mattered. Oumuamua was fading rapidly as it moved farther from both the Sun and Earth. Telescopes around the world scrambled to grab observation time. Hubble interrupted its scheduled observations. The Very Large Telescope in Chile pivoted. The Gemini Observatory cleared its schedule. Everyone wanted data before this once-in-a-lifetime opportunity vanished. But observation time on major telescopes is allocated months in advance. You can't just call up and say, "Hey, can I use the Hubble tonight?" There are protocols, committees, scheduling conflicts. Getting emergency observation time requires convincing directors that your target is worth bumping other scheduled projects. For Oumuamua, that argument was easy. This was literally the first interstellar object ever detected. But the logistics still took days. Days they didn't have. By mid-November, Oumuamua had faded to magnitude 23, barely visible even to the largest telescopes. By December, it was gone. Astronomers had captured maybe 80 hours of total observation time across all instruments worldwide. That's it. 80 hours to study an object that had travelled for millions of years to reach us. What could they have done with more time? Everything. High-resolution spectroscopy to determine precise surface composition. Radar observations to directly measure its shape instead of inferring it from brightness variations. Long baseline interferometry to detect outgassing at levels below visual detection thresholds. Detailed thermal imaging to map temperature variations across its surface. All of that requires extended observation periods. All of that was impossible. Karen Meach, who led the discovery team, later told Nature, "We missed the chance of a lifetime. If we had detected it even 2 weeks earlier, we could have answered so many questions. Instead, we're left with mysteries we may never solve." The mission proposals came too late. NASA's Jet Propulsion Laboratory quickly sketched out a spacecraft concept that could have intercepted Oumuamua using existing technology, launch within weeks, use gravitational assists from Earth and Jupiter, catch up to the object within a few years. The physics worked, the engineering was feasible, but you can't design, build, and launch a spacecraft in weeks. By the time anyone seriously considered an intercept mission, Oumuamua was already too far away. The launch window had closed. Then came 2I/Borisov, and everything changed. Gennady Borisov discovered it on August 30th, 2019, when it was still 3 astronomical units from the Sun 3 times farther than Earth's orbit. It was inbound, approaching it. Astronomers had months, not weeks, months to coordinate observations, months to gather data, months to actually do science properly. The difference was staggering. Where Oumuamua got 80 hours of total observation time, Borisov received thousands of hours across dozens of telescopes. The Hubble Space Telescope observed it repeatedly from October 2019 through March 2020. The Atacama Large Millimeter Array captured detailed spectra of its coma composition. The Very Large Telescope used adaptive optics to resolve the nucleus and track jet activity. Amateur astronomers worldwide contributed observations, building up a continuous monitoring record that professional observatories alone couldn't match. This is what proper astronomical study looks like. Not frantic data grabs in a race against fading light, but methodical, repeated observations that build a comprehensive picture over time. Scientists could track how Borisov's activity changed as it approached the Sun, peaked at perihelion, and then declined as it receded. They could compare observations from different instruments and cross-validate their results. They could plan follow-up observations based on initial findings. Dr. Bin Yang from the European Southern Observatory, who coordinated some of the VLT observations, emphasized the difference. With Borisov, we had the luxury of time. We could optimize our observing strategy, test different instrumental configurations, and really understand what we were seeing. That's how science is supposed to work. The data quality reflected that luxury. While Oumuamua's shape is still debated based on limited brightness measurements, Borisov's nucleus size is known to within 50 meters, while Oumuamua's composition remains speculative. Borisov's chemical inventory is documented in peer-reviewed papers with high confidence. The difference between rushed observation and careful study is the difference between a blurry snapshot and a high-resolution photograph. But even Borisov had limitations. It never came particularly close to Earth at its nearest approach. In late December 2019, it was still over 300 million kilometers away, roughly twice the distance to the Sun. That's far. Too far for detailed surface imaging. Too far for radar observations. Too far to detect anything but the strongest spectral lines. Astronomers got good data, but not great data. They characterized Borisov thoroughly, but they couldn't study it intimately. And still, nobody sent a spacecraft. There was time, theoretically. ESA briefly considered a mission using technologies developed for Comet Interceptor, a planned mission to visit a long-period comet. But Comet Interceptor itself wasn't scheduled to launch until 2029, and the spacecraft design wasn't finalized. You can't launch a spacecraft that doesn't exist. Borisov came and went, observed but not visited, understood but not touched. Now here we are with 3I/Atlas, and the pattern is repeating. Early detection. Yes, better than Oumuamua, but still not early enough for the mission. Still not enough lead time to do anything except point telescopes and watch. We're trapped in this cycle of observation without interaction, studying these objects from afar like naturalists watching rare birds through binoculars, never able to get close, never able to truly understand. The technology gap is closing, though in 2017 our detection systems barely caught Oumuamua. In 2019 an amateur astronomer with a backyard telescope found Borisov. In 2025 the automated Atlas system flagged 3I/Atlas immediately. We're getting better at finding these objects. The Vera Rubin Observatory, which achieved first light earlier this year, will scan the entire visible sky every few nights with a camera so powerful it could spot a candle flame from thousands of miles away. When it reaches full operational capacity, scientists estimate it will detect dozens of interstellar objects every year, maybe more. Detection is improving, but detection isn't enough. What good is spotting these cosmic messengers if all we can do is wave as they pass by? What frustrates scientists most isn't that we can't see interstellar objects, it's that we can see them just well enough to know what we're missing. Every observation reveals a dozen new questions we can't answer without closer study. Every spectrum shows tantalizing hints of composition we can't confirm without direct sampling. Every trajectory calculation shows an object we can't catch. And the clock is always ticking. Right now. 3I/Atlas is approaching perihelion. Right now, it's getting brighter, more active, more observable, but in a few months it will begin fading. In a year, It'll be beyond the reach of all but the largest telescopes. In 2 years, it will be gone. Another visitor that came showed us mysteries and left before we could solve them. Unless we change how we approach this problem, unless we stop simply observing and start preparing to intercept, because the data these objects could provide, if we could actually reach them, touch them, sample them, would revolutionize our understanding of planetary formation, interstellar chemistry, and the diversity of objects wandering between the stars. The question is whether we're ready to take that step, and what those samples might actually tell us. What do these visitors actually tell us about the universe beyond our solar system? That's the billion-dollar question. Because these aren't just interesting astronomical curiosities, they're physical samples, messengers carrying information about places we can't visit, star systems we can't observe directly, and planetary formation processes happening light years away. Start with the most fundamental revelation: other solar systems work like ours. Before Borisov, that wasn't certain. Sure, we discovered thousands of exoplanets using transit methods and radial velocity measurements. We knew other stars had planets, but we'd never actually seen material from those systems. We'd never analysed the composition of objects formed around other stars. Theory suggested they'd be similar to our own solar system, same physics, same chemistry, same materials, but theory and observation are different things. Borisov confirmed the theory: its water to carbon monoxide ratio, its dust composition, its organic molecules all consistent with comets from our Oort cloud. That's profound. It means the icy building blocks that formed planets around another star, possibly billions of years ago, are chemically similar to the icy building blocks that formed our planets. The universe isn't wildly diverse in its planetary construction materials. It's remarkably uniform. Dr. Martin Cordner from NASA's Goddard Space Flight Center, who studied Borisov's cyanide emissions, explained the significance. The presence of cyanide in similar abundances to solar system comets suggests that the fundamental chemistry of planet formation, the molecules available, the temperatures at which they condense, the reactions they undergo is universal. We're not special. Our solar system formed following the same rules as countless others. That uniformity has huge implications. It means the processes we study here, how planets form from protoplanetary disks, how volatiles get distributed through a forming solar system, how gravitational interactions shape the architecture of planetary systems, those processes apply everywhere. Every observation we make of our own solar system's formation history is potentially applicable to understanding how planets form around other stars. But then there's the diversity. Because while Borisov proved similarity, Oumuamua and 3I/Atlas prove that not everything out there follows the same pattern. Oumuamua's extreme elongation, for instance. How does something like that Form 1 hypothesis suggest tidal disruption? Perhaps Oumuamua passed extremely close to a star or massive planet, and gravitational tidal forces stretched it like taffy before flinging it into interstellar space. That would require a very specific close encounter, something rare but not impossible. Another idea proposes it formed through collision. Two objects smashing together, fragmenting, with Oumuamua being one shard flung outward at high speed. Collisions in planetary systems are common during the early chaotic phase when planets are still forming and orbits haven't stabilized. Our moon likely formed from a giant impact between Earth and a Mars-sized object. Why couldn't interstellar objects form the same way? But here's the interesting part. Both scenarios, tidal disruption and collision, tell us something about the dynamics of other planetary systems. If Oumuamua was tidally stretched, its home system must have had massive planets in orbits that allowed close gravitational encounters. If it was a collision fragment, its home system went through a violent phase of planetary formation. Either way, we're learning about events that happened in another solar system, possibly billions of years ago, by studying this one weird object that wandered past us, and 3I/Atlas, that multicolored glow, that extreme activity it's telling us about volatile inventories in the outer regions of other solar systems. Remember, comets form in the cold outer zones of planetary systems, beyond the frost line where water and other volatiles can condense into solid ice. The specific mix of ices, how much water versus carbon monoxide versus ammonia versus methane, depends on the temperature gradient in that outer region, which depends on the luminosity of the parent star, the architecture of the planetary system, and the timing of planet formation. 3I/Atlas's composition, once we fully analyse it, will reveal details about the conditions in its birth system. Was its parent star hotter or cooler than our Sun? Were there giant planets in its outer system that affected temperature distributions? Did it form early in its system's history when volatiles were more abundant? Or later, after much of the available material had already been incorporated into planets? Think about what that means. We're reverse engineering alien solar systems from single data points. It's like finding a single rock on a beach and using its mineral composition to deduce details about the mountain range it eroded from, the tectonic activity that formed that range, and the climate that weathered it. Except the mountain range is a solar system light years away, and the rock travelled through interstellar space for millions of years to get here. But there's another layer to this. These objects don't just tell us about where they came from, they tell us about the journey itself, about what happens to material during millions of years of interstellar travel. Cosmic rays are the key. In interstellar space, far from any star's protective magnetic field, objects are bombarded constantly by high-energy particles, protons, atomic nuclei, even occasional electrons travelling at nearly the speed of light. These cosmic rays slam into surface materials, breaking chemical bonds, creating new compounds, altering colour and texture. That deep red colour on both Oumuamua and Borisov, that's cosmic ray damage. Complex organic molecules, hydrocarbons, tholins, other carbon-based compounds get hit by radiation and chemically transform into reddish materials. The longer an object spends in interstellar space, the deeper and more extensive that radiation damage becomes. It's like cosmic tanning, except instead of UV light, it's high-energy particles, and instead of skin, it's frozen organic compounds. Scientists can use that radiation damage as a clock. By measuring the extent of chemical alteration and knowing the typical cosmic ray flux in interstellar space, they can estimate how long an object has been wandering between stars. For Borisov, estimates suggest tens of millions of years minimum, possibly longer. For Oumuamua, similar timeframes. These aren't young objects. They're ancient wanderers, ejected from their home systems long before humans existed, travelling through the void for longer than mammalian species have existed on Earth. And during that journey, they've been exposed to conditions we can barely simulate in laboratories. Temperatures within a few degrees of absolute zero. Perfect vacuum. Constant radiation bombardment. No protective atmosphere, no magnetic field. Nothing but raw cosmic environment acting on raw material for millions of years. What does that do to ice, to rock, to organic molecules? We're only beginning to understand. There's also the question of contamination, or rather, the lack of it. These objects travelled through interstellar space without ever entering another solar system's inner regions. They weren't heated by another star. They weren't hit by solar wind from another sun. They're pristine in a way that solar system objects aren't. Even our most primitive meteorites, even comets from the Oort cloud, have been shaped by our sun's influence since the solar system formed. But interstellar objects, they're snapshots of raw planetary formation material, frozen in time, preserved by the cold emptiness of space. That makes them invaluable for understanding what planets are made of at the most fundamental level. When you study a solar system comet, You're studying material that's been processed by billions of years in the Sun's environment. When you study an interstellar comet, you're studying material from a completely different environment, a different star, different planets, different formation conditions that's been preserved through its interstellar journey. Dr. Amaya Moro-Martin from the Space Telescope Science Institute described it perfectly in a 2020 paper. Interstellar objects are natural space probes, carrying information about the composition and dynamics of exoplanetary systems directly to our doorstep. Each one is a data point in a grand survey of planetary systems across the galaxy. A grand survey. That's exactly what this is. Every interstellar visitor is one more sample, one more piece of the puzzle. 3 objects aren't enough to draw sweeping conclusions, but they're a start. They've shown us that some things are universal basic chemistry, fundamental physics, while other things vary wildly shapes, activity levels, compositions. And here's the beautiful part this survey is only beginning. The Vera Rubin Observatory, once fully operational, will detect an estimated 20 to 50 interstellar objects per year, maybe more, in a decade. We could have hundreds of data points. In a century, thousands, each one teaching us something new about planetary systems across the galaxy, about the diversity of objects out there, about the cosmic neighborhood we inhabit. But detection alone isn't enough. Observation from afar only tells us so much. To truly understand these messengers, to unlock the full library of information they carry, we need to do something more ambitious. We need to intercept them, touch them, and that requires technology and planning that's already in motion. The European Space Agency has a spacecraft waiting. Right now, in an engineering facility, a mission called Comet Interceptor sits in development, designed specifically to do what we failed to do with Oumuamua and Borisov, actually reach an interstellar visitor. The concept is brilliant in its simplicity. Instead of launching a mission after discovering a target, you launch the mission first and park it in space, waiting. The spacecraft will sit at the Sun-Earth Lagrange point 2L2 for short, a gravitationally stable location about 1.5 million kilometers from Earth in the opposite direction from the Sun. At L2, the combined gravity of the Earth and Sun creates a sweet spot where a spacecraft can hover indefinitely with minimal fuel expenditure, like a marble balanced perfectly in a cosmic bowl. And there it will wait, for years if necessary, until ground-based telescopes detect an incoming long-period comet, or the real prize, another interstellar object. When that happens, Comet Interceptor will fire its engines, leave L2 and race toward the target, arriving in time to conduct a close flyby, deploying instruments to analyze composition, capture images, measure magnetic fields, and collect data that's impossible to gather from Earth. The mission is scheduled to launch in 2029 as a co-passenger on ESA's Aerial Exoplanet Observatory. That's 4 years away. 4 years until we have a spacecraft on standby, ready to respond within weeks to any interstellar visitor that wanders through. Geraint Jones from University College London. The mission's lead scientist described the strategy. We're moving from reactive to proactive. Instead of watching these objects disappear while we scramble to organize a mission, we'll already have hardware in position, ready to intercept. But here's the challenge: Comet Interceptor wasn't designed for the fastest interstellar objects. Its delta-V budget, the total velocity change it can achieve with onboard fuel, is optimized for slow-moving, long-period comets entering the inner solar system for the first time. Objects travelling maybe 10 to 20 kilometers per second relative to the Sun. It could potentially reach something like Borisov, which moved at 32 kilometers per second, but Oumuamua at 26 kilometers per s possibly, depending on trajectory. 3I/Atlas at potentially 40 kilometers per s, that's pushing it. The encounter would be fast regardless. You're not landing on these things. You're not even slowing down to orbit them. You're conducting a high-speed flyby, Instruments blazing, cameras clicking, spectrometers analysing, all within minutes or even seconds as you scream past at relative velocities of tens of kilometres per second. At 30 kilometres per second relative velocity, you'd cover the distance from New York to Los Angeles in under 2 minutes. That's how fast these intercepts happen. But even a seconds-long flyby at close range beats months of telescope observations from millions of kilometres away. Rosetta, which orbited Comet 67P for 2 years, revolutionised our understanding of comets by getting close, by touching the surface with its Philae lander, by smelling the outgassing with in-situ instruments. Imagine doing even a fraction of that with an interstellar object. The science return would be phenomenal. Comet Interceptor will carry 3 separate spacecraft, a main probe, and 2 smaller subprobes that will separate during the approach, allowing observations from multiple angles simultaneously. One probe might fly through the coma, sampling gases and dust directly. Another might approach the nucleus for close-up imaging. The main spacecraft coordinates everything, collecting data and transmitting it back to Earth. It's a shotgun approach. Maximize the chance that at least one probe captures critical data, even if conditions aren't perfect. The design was finalized based on lessons learned from Oumuamua and Borisov. Scientists now understand they need flexibility, rapid response capability, and instruments that can function during extremely brief encounters. Traditional comet missions like Rosetta or Deep Impact had months to study their targets. Interstellar missions might have minutes. Every sensor, every camera, every spectrometer needs to work perfectly in that fleeting window. But what if Comet Interceptor isn't enough? What if we need something faster, more capable, able to chase down objects moving at 50 or 60 kilometers per second? Enter Project Lyra, a concept mission studied by the Initiative for Interstellar Studies. Lyra isn't funded. It's not even formally proposed. It exists only as engineering studies and scientific papers. But the concept is tantalizing: a dedicated interstellar object interceptor capable of reaching extremely high velocities through a combination of solar flybys, planetary gravity assists, and advanced propulsion. The mission would work like this: launch toward the Sun on an elliptical orbit, swing extremely close to the solar surface, closer than any spacecraft has ever gone, and use the intense gravitational acceleration to slingshot outward at tremendous speed. Add gravity assists from Earth or Jupiter, and you could theoretically reach velocities exceeding 70 kilometers per second. That's fast enough to catch almost any interstellar visitor we're likely to detect. Adam Hibbard, one of the researchers behind Project Lyra, published calculations in 2017 showing that a mission could have caught Oumuamua if launched within a year of discovery. The trajectory was insane: multiple gravity assists, a solar flyby within 3 solar radii of the Sun's surface, speeds that would make it one of the fastest human-made objects ever. But the physics worked. The technology exists, at least in principle. The problem: cost and risk. Solar flybys that close require heat shields beyond anything currently operational. The Parker Solar Probe, humanity's closest solar approach, gets within 6.2 million kilometers of the Sun's surface and requires a carbon composite shield 11.4 centimeters thick. Project Lyra would need to go twice as close, enduring temperatures exceeding 2000 degrees Celsius. That's technically possible, but expensive and risky. And there's another issue: time. Even with Project Lyra's speed, catching an interstellar object requires years of travel. Launch in 2026, arrive in 2030 or 2031. By then, the target might be too far from the Sun to observe clearly. Its activity shut down, its surface frozen again. You'd still get valuable data: close-up images, surface composition, maybe even a sample if you include a collection mechanism, but you'd miss the dynamic phase, the active outgassing, the jets and plumes. That's why some scientists are proposing something even more ambitious: pre-positioned interceptor swarms. Imagine not one spacecraft at L2 but dozens scattered throughout the solar system at various Lagrange points, in solar orbit at different distances, positioned strategically to minimize response time to any incoming object from any direction. When an interstellar visitor is detected, the nearest spacecraft activates, calculates an intercept trajectory, and launches immediately. It's science fiction today. But is it science fiction forever? The cost would be enormous, billions of dollars to place multiple spacecraft on permanent standby. But the scientific return would be transformative. We'd go from lucky occasional encounters to systematic interception of every detectable interstellar object. We'd build a comprehensive library of compositions, structures, and properties. We'd finally understand whether the 3 visitors we've seen so far are representative or exceptional. Dr. Michelle Bannister, reflecting on the future of interstellar object studies, put it this way: we're at the beginning of a new era. In 10 years, with better detection and dedicated interceptor missions, we might routinely visit these objects. In 50 years, intercepting interstellar visitors could be as common as sending probes to comets is today. We're witnessing the birth of a new branch of space exploration. But we don't have to wait 50 years to learn more. Right now, as you're watching this, observatories worldwide are tracking 3I/Atlas, gathering data, analyzing its trajectory, studying its composition. The Vera Rubin Observatory is scanning the sky every few nights, searching for the next visitor. Amateur astronomers are contributing observations, building up data sets that complement professional research. This is happening now. The era of interstellar astronomy isn't some distant future dream. It's here. We've detected 3 visitors. We'll detect more. And each one will teach us something new about the galaxy we inhabit, the planetary systems scattered across it, and the countless objects drifting between the stars. But beyond the science, beyond the technology, beyond the missions and telescopes and spacecraft, there's something profound happening here, something that changes how we see our place in the universe. And that shift in perspective might be the most important discovery of all. For most of human history, we believed we lived in a closed system. Our solar system was an island, isolated in space, completely separate from every other star and planet in the universe. Sure, we could see those other stars. We could measure their light, calculate their distances, even detect planets orbiting them. But they were fundamentally unreachable, untouchable, knowable only through the photons they emitted. Interstellar objects changed that forever. When Oumuamua arrived in 2017, it didn't just bring us an unusual rock to study. It brought us physical evidence that our solar system is connected to the rest of the galaxy in ways we'd never appreciated. The space between stars isn't empty void. It's a network, a cosmic highway where material flows constantly, objects ejected from one system eventually wandering into another, carrying information across light years and millions of years. Think about what that means on a human level. Right now, somewhere in our solar system, maybe beyond Neptune, maybe closer, there are objects from other stars, objects that formed around suns we can see in our night sky, material that was once part of planetary systems where alien worlds orbit, where different physics play out on different scales, where the history of formation and evolution followed paths we're only beginning to imagine. And it goes both ways. Our solar system ejects objects too. Jupiter, with its immense gravity, has been flinging comets and asteroids into interstellar space for billions of years. Saturn contributes. Neptune contributes. Close gravitational encounters during the chaotic early days of planetary formation scattered material everywhere, some of it achieving escape velocity, leaving our solar system forever. Where did those objects go? They're out there now, wandering. Some might have already entered other star systems. Some might be approaching planetary systems right now, about to be detected by alien astronomers if such astronomers exist, who will look at these visitors from our sun and wonder what our solar system is like, what planets we have, what conditions existed here billions of years ago. We're not isolated. We're part of a galactic ecosystem where material circulates, where objects travel between systems, where the boundaries we imagine don't really exist. Carl Sagan famously said we're made of star stuff. The atoms in our bodies were forged in stellar furnaces and scattered by supernova explosions. But it's deeper than that. We're made of solar system stuff. Material that formed here but could just as easily have formed somewhere else and arrived here as an interstellar visitor billions of years ago. Some scientists even propose that life itself might travel this way. Panspermia, the hypothesis that life originated elsewhere and arrived on Earth via comets or asteroids, is controversial but not implausible. We know microorganisms can survive extreme conditions. We know organic molecules exist on comets. We know impacts from space objects can deliver material to planetary surfaces. Could life have started on an ancient planet orbiting a now dead star, gotten ejected during a planetary collision, spent millions of years frozen in an interstellar comet, and arrived on early Earth to seed the biology that eventually produced us? It sounds like science fiction, but the physics works, the chemistry works, the timescales work. We don't have proof, but we also can't rule it out. And every interstellar visitor we study gives us more data to assess that possibility. If we found amino acids on an interstellar object, complex organic molecules arranged in ways that suggest biological origin, it would revolutionize everything. We'd have evidence that life exists or existed elsewhere, and that it can travel between star systems. But even without that discovery, the implications are staggering. Every star system in the galaxy is ejecting material. Trillions of objects are wandering through interstellar space right now. And they're not just wandering, they're mixing. Material from ancient star systems gets incorporated into new ones. Elements forged in one stellar environment become part of planets forming around different stars. The galaxy is constantly stirring itself, redistributing matter, ensuring that no system remains truly isolated. Dr. Oumuamua Martin described this beautifully in a 2019 paper. Interstellar objects represent the connective tissue of the galaxy. They link stellar systems across vast distances and timescales, creating a web of material exchange that has been ongoing since the galaxy formed. We are part of that web, and so is every other planetary system. A web. That's the perfect metaphor. We're not alone on an island. We're nodes in a network that spans the entire galaxy. And we're only now beginning to understand what that network looks like, how it functions, how much traffic flows through it. The statistics are mind-boggling. Based on the detection rate of just 3 objects in 8 years, astronomers now estimate there could be millions of interstellar objects in our solar system at any given time. Millions. Most are small pebbles, boulders, maybe car-sized, too small and too dark to detect. But they're there, passing through, some staying for centuries in long, slow orbits before eventually being perturbed out, others zipping through in months, and this has been happening forever. For 4.6 billion years since our solar system formed, interstellar visitors have been arriving, passing through, leaving. Some may have impacted planets, some may have been captured into orbit, some may still be out there in the Oort cloud, indistinguishable from objects born here, waiting to be discovered. What does that do to our sense of place for centuries? We thought Earth was the centre of everything. Then we learned we orbit the Sun. Then we learned the Sun is one of billions of stars in our galaxy. Then we learned our galaxy is one of trillions in the universe. Each discovery made us smaller, less significant, more isolated, But interstellar objects reverse that isolation. They tell us we're connected. We're not alone on a cosmic island. We're part of something larger, something dynamic, something that links us to the rest of the galaxy in tangible, physical ways. There's something deeply comforting about that. We're participants in a galaxy-wide exchange of matter and information that's been ongoing for billions of years. And we're entering a new phase of that participation. For all of human history, we've been passive recipients. Objects arrived. We didn't know where they came from. We couldn't study them properly. But starting with Comet Interceptor in 2029, we're becoming active participants. We're preparing to intercept these visitors, study them up close, learn their secrets. We're moving from ignorance to understanding, from observation to interaction. The Vera Rubin Observatory will soon be detecting dozens of interstellar objects every year. Within a decade, we might catalogue hundreds. Within a century, thousands. Each one will be tracked, studied, some intercepted by spacecraft, their compositions analysed, their origins traced as best we can. We'll build a comprehensive census of what's travelling between stars, what materials are common, what's rare, how different stellar systems compare. Can you imagine what that knowledge will look like in 100 years? Picture a database containing detailed information on thousands of interstellar visitors, their sizes, shapes, compositions, trajectories, estimated ages, possible origins. Picture comparative studies that reveal patterns. Objects from metal-rich stars look like this. Objects from young stellar systems behave like that. Objects that travel through dense interstellar clouds show these characteristics. Picture discoveries we can't yet imagine because we don't have enough data to know what questions to ask. That's the future we're building toward. From 0 detections before 2017 to 3 by 2025, and soon dozens per year. Then hundreds. The exponential growth of interstellar astronomy is beginning now. We're living through the opening chapter of a story that will unfold across generations. And it starts with 3 visitors. Oumuamua, the mysterious scout that arrived too fast to study but changed everything by proving these objects exist. Borisov, the familiar comet that showed us interstellar objects can be normal, understandable, consistent with our theories. And 3I/Atlas, the multicoloured enigma that's teaching us there's still so much we don't understand. So many surprises waiting in the cosmic dark. 3 messengers from other stars. 3 ambassadors from distant solar systems we'll never visit. 3 physical samples of the galaxy beyond our own neighbourhood, delivered to our doorstep by the patient mechanics of orbital dynamics and time. They came from the dark. They'll return to the dark. But while they're here, while they're visible, they're teaching us that we're not alone on an island. We're part of a connected galaxy, vast and ancient and full of wonders we're only beginning to explore. The next visitor is already on its way. We just haven't detected it yet.